The Graveyard of Dead Stars. What happens after stars die. Warm welcome, hello, and welcome back to Sleep Science Chronicles. Whether you're settling in for the night, resting your eyes after a long day, or simply looking for a quiet place to let your mind wander, you've found the right place. There's no rush here, no deadlines, no noise. Just you and the sound of these words, and the slow unfolding of something beautiful. Tonight, we're going somewhere vast and quiet. Somewhere most people never think to look. We're going to the places where stars go after they die. You've probably seen pictures of stars being born. Those glowing nurseries of gas and light, swirling with color, bursting with energy. But what happens after? What happens when a star has burned through its fuel, when its light begins to fade, when the fire that sustained it for millions or even billions of years finally begins to go out? The answer is not silence. The answer is not darkness, at least not right away. What comes after the death of a star is one of the most extraordinary, varied, and quietly beautiful chapters in all of physics. Some stars collapse into objects so dense that a teaspoon of their material would weigh more than a mountain. Some explode with a violence that outshines entire galaxies. Some leave behind glowing shells of gas that drift through space like cosmic lanterns. And some, the most patient of all, begin a cooling process so slow that the universe itself has not yet existed long enough for even a single one to finish. Tonight, we'll visit all of them. Gently, one wonder at a time. Some of these facts will be familiar, many will not. All of them are true, drawn from the best observations and research humanity has gathered over centuries of staring upward and asking what the stars are made of. So let yourself settle in. Adjust your pillow if you need to. Let your shoulders drop. Let your breathing slow. And when you're ready, we'll begin. Topic: invitation. The universe is, in many ways, a graveyard. Not a sad one, not a cold one, but a graveyard all the same. Vast and ancient and filled with the remains of things that once burned. Every point of light you see in the night sky is a star in the middle of its life, fusing hydrogen or helium or heavier elements in its core, radiating energy outward into the dark. But for every star you can see, there are countless others that have already finished. Their light has faded. Their fuel is spent. And what remains of them now drifts or spins or collapses in the spaces between the living stars. These remnants take many forms. Some are small and white and slowly dimming, like embers left behind after a campfire. Some are impossibly dense and spinning hundreds of times per second, sending beams of radiation sweeping across the cosmos like lighthouses. Some have crushed themselves into points of infinite density, warping space and time so severely that not even light can escape. And some have scattered themselves across light years of space, painting the void with color and chemistry. Tonight, we'll explore them all. We'll begin with the most common and gentle of stellar deaths and gradually make our way toward the most extreme. Along the way, you'll discover that death, in the language of the cosmos, is not an ending. It is a transformation. Every dead star leaves something behind, and those remnants, those ghosts of ancient fires, shape the universe in ways that make your own existence possible. This is the graveyard of dead stars, and it is full of wonder. Soft CTA. If these calm explorations of the universe help you unwind, or if they've ever carried you gently into sleep, a quiet like or a tap on subscribe would mean the world. It helps other restless minds find their way here too. One sleepy soul at a time. Now, let's begin. Before we visit the remnants, it helps to understand what brings a star to its final chapter. And it all begins with a simple truth. Stars are not eternal. They are born, they burn, and eventually, they run out of fuel. Every star in the universe is powered by nuclear fusion, the process of pressing lighter atomic nuclei together under extreme heat and pressure until they merge into heavier ones, releasing enormous amounts of energy in the process. In most stars, this begins with hydrogen, the simplest and most abundant element in the cosmos. Deep in a star's core, where temperatures reach millions of degrees and gravitational pressure is immense, hydrogen nuclei, single protons, collide and fuse into helium. Each fusion event releases a tiny burst of energy. But when you multiply that by the trillions upon trillions of reactions happening every second, the result is the sustained glow of a star. Our own sun converts roughly 600 million tons of hydrogen into helium every single second. It has been doing this for approximately 4.6 billion years, and it has enough hydrogen left in its core to continue for roughly another 5 billion years. That sounds like a long time, and it is. But it is not forever. Eventually, the hydrogen will run low. What happens next depends almost entirely on one thing: how massive the star is. Mass is the single most important factor in determining not just how a star lives, but how it dies. A small star and a massive star may begin their lives in similar ways, but their endings are profoundly different. As different as a candle burning down quietly and a building being struck by lightning. Stars like our sun, sometimes called yellow dwarfs, are considered medium-sized. They are not the largest stars in the universe, nor the smallest. They burn steadily for billions of years, fusing hydrogen into helium in their cores. When the hydrogen begins to run out, the core contracts and heats up, and the star begins fusing helium into carbon and oxygen. During this phase, the outer layers of the star expand dramatically, and the star becomes a red giant, a swollen, luminous version of its former self. Our sun, when it reaches this stage in roughly 5 billion years, will expand so much that it will likely engulf Mercury and Venus, and possibly Earth as well. But a red giant is not the end. It is the beginning of the end. The star continues to burn through its available fuel, but for a medium-mass star like the Sun, the temperatures and pressures in the core never become high enough to fuse elements heavier than carbon and oxygen. The fusion reactions slow. The outer layers of the star, no longer held in place by the outward pressure of fusion, begin to drift away into space. They form a shell of glowing gas, a planetary nebula that expands outward, illuminated by the hot core that remains behind. And that core, now exposed and compressed, is what we call a white dwarf. Stars much more massive than our sun follow a different path. They burn hotter and faster, fusing hydrogen into helium, helium into carbon, carbon into neon, neon into oxygen, oxygen into silicon, and finally silicon into iron. Each stage of fusion produces less energy than the last, and each stage lasts for a shorter time. A massive star might spend millions of years fusing hydrogen, but only days fusing silicon into iron. And when iron fills the core, fusion stops entirely. Iron cannot be fused to release energy. It absorbs energy instead. The core loses its support, and in a fraction of a second, it collapses under its own gravity. The result is a supernova, one of the most violent and luminous events in the known universe. What remains after a supernova depends, once again, on mass. If the collapsing core is below a certain threshold, roughly 3 times the mass of our sun, it becomes a neutron star, one of the densest objects in existence. If it exceeds that threshold, nothing can stop the collapse, and the core becomes a black hole, a region of space-time so warped that nothing, not even light, can escape from it. These are the broad strokes, but within each of these endings lies a universe of detail, strangeness, and beauty. And that is where we're headed now. The first thing worth knowing is that the mass of a star is set very early in its life. When a cloud of gas and dust begins to collapse under gravity, a process called stellar formation, the amount of material that gathers together determines the mass of the resulting star. A small clump produces a small star. A massive clump produces a massive one. And from that moment on, the star's fate is essentially sealed. Its mass determines how hot it will burn, how long it will live, what elements it will create in its core, and what kind of remnant it will leave behind when it dies. This is sometimes called the initial mass function, and it reveals something surprising. Most stars in the universe are small. The most common type of star is not a giant or a supergiant, but a red dwarf, a cool, dim, low-mass star that burns its hydrogen so slowly that it can last for trillions of years. Red dwarfs make up roughly 70 to 80% of all stars in the Milky Way. And because they burn so slowly, not a single red dwarf that has ever formed in the history of the universe has yet died. They are all still burning. Their graveyards are empty. The stars that do die, the ones that have already exhausted their fuel, tend to be the brighter, more massive ones. And their remnants are what fill the cosmic graveyard we're exploring tonight. White dwarfs, neutron stars, black holes, and the vast expanding shells of gas and dust they leave behind. Each one a monument to a fire that once burned and then, in its own way, went out. There is something quietly humbling about this. The stars that shine the brightest are the ones that die the soonest. A blue supergiant, 10 or 20 times the mass of our sun, may live for only a few million years before exploding. Our sun will last for 10 billion, and the smallest red dwarfs may burn for 10 trillion years or more, long after the last galaxy has faded and the universe has grown cold and dark. In the cosmos, patience and brightness are inversely related. The most dazzling lives are often the shortest, and the longest-lived stars are the ones you can barely see. When a star like our sun reaches the end of its life, it does not explode. It does not tear itself apart. Instead, it exhales. Slowly, gently, it releases its outer layers into space, and what remains is a small, hot, incredibly dense object called a white dwarf. These are the most common stellar remnants in the universe, and they are among the most quietly extraordinary. A typical white dwarf is roughly the size of Earth, about 12,000 kilometers in diameter. But it contains nearly the entire mass of the star it once was. Our sun, for example, will one day become a white dwarf with a diameter similar to Earth's, but a mass roughly equal to what the sun has now. This means that the material inside a white dwarf is compressed to extraordinary density. A single teaspoon of white dwarf matter would weigh approximately 5.5 tons, about as much as an elephant. This density is not held up by any kind of active burning or fusion. The white dwarf is no longer generating energy. Instead, it is supported by something called electron degeneracy pressure, a quantum mechanical effect that arises because electrons, the tiny particles orbiting atomic nuclei, resist being squeezed too closely together. It is not a force in the traditional sense. It is a consequence of the Pauli exclusion principle, which states that no two electrons can occupy the same quantum state. In a white dwarf, the electrons have been compressed so tightly that this quantum resistance is the only thing preventing further collapse. The surface temperature of a newly formed white dwarf can be extraordinarily high, sometimes exceeding 100,000 degrees Celsius. This makes young white dwarfs intensely luminous in ultraviolet light, even though they are small. But because they are no longer generating energy through fusion, they have no way to replenish the heat they radiate. And so, slowly, over billions of years, they cool. This cooling process is remarkably slow. A white dwarf that formed 10 billion years ago, around the time our sun was born, would still be warm today. It would still be glowing faintly, emitting visible light and heat into the cold of space. Astronomers have used the cooling rates of white dwarfs to estimate the ages of star clusters and even the age of the Milky Way's disk itself. They are, in a sense, cosmic clocks, ticking not with movement but with the slow, steady loss of warmth. The composition of a white dwarf depends on the star it came from. Most white dwarfs are made primarily of carbon and oxygen, the products of helium fusion in the star's red giant phase. These are called carbon-oxygen white dwarfs, and they are the most common type, but some, formed from less massive stars that never reached helium fusion, are made primarily of helium. And a rare few, formed from the most massive stars that can still avoid a supernova, are made of oxygen, neon, and magnesium. Regardless of composition, all white dwarfs share one defining trait. They are slowly dying. Not in the dramatic sense of a supernova, but in the quiet sense of a fire that has stopped being fed. They glow with the residual heat of their former lives, and as the eons pass, that glow fades. First from white to yellow, then from yellow to orange, then from orange to red, and eventually, in theory, to black. There is a limit to how massive a white dwarf can be. This limit, known as the Chandrasekhar limit, is approximately 1.4 times the mass of our Sun. It was calculated in 1930 by the Indian astrophysicist Subramanian Chandrasekhar, who was just 19 years old at the time. He showed that if a white dwarf exceeds this mass, the electron degeneracy pressure that supports it is no longer sufficient. The star would collapse further, into a neutron star, or, if massive enough, a black hole. This discovery was initially met with resistance from established astronomers, but it has since been confirmed as one of the foundational results of stellar astrophysics. Some white dwarfs exist in binary systems, orbiting closely with another star. In these systems, the white dwarf's gravity can pull material from its companion, slowly accumulating a layer of hydrogen or helium on its surface. When this layer reaches a critical mass and temperature, it ignites in a thermonuclear explosion, producing a sudden and dramatic increase in brightness. This is called a nova, not to be confused with a supernova, which is far more energetic. A nova can increase a white dwarf's brightness by a factor of 50,000 to 100,000 for a few weeks before fading again. And because the white dwarf itself is not destroyed, the process can repeat, sometimes multiple times over thousands of years. In rarer cases, the accumulation of material can push the white dwarf over the Chandrasekhar limit, or two white dwarfs in a binary system can spiral together and merge. When this happens, the result is a Type 1a supernova, an explosion so consistent in brightness that astronomers use them as standard candles to measure distances across the universe. It was the study of Type 1a supernova in the late 1990s that led to the discovery that the expansion of the universe is accelerating, one of the most profound discoveries in modern cosmology. The oldest white dwarfs in the Milky Way are estimated to be around 11 to 12 billion years old. They have been cooling since before our sun existed, since before our solar system formed, since the galaxy was young and still assembling itself from colliding dwarf galaxies. And still, they glow. Faintly, but persistently. One of the nearest white dwarfs to Earth is Sirius B, the companion of Sirius, the brightest star in the night sky. Sirius B was discovered in 1862 and was one of the first white dwarfs ever identified. It has a mass roughly equal to our Sun's, but a diameter only slightly larger than Earth's. Its surface temperature is approximately 25,200 degrees Celsius, and it has been cooling for an estimated 120 million years. In the night sky, it is invisible to the naked eye, hidden in the glare of its brilliant companion. But it is there, a dense, hot, ancient ember slowly fading. White dwarfs are sometimes surrounded by the remnants of planetary systems. As a star evolves into a red giant and then sheds its outer layers, any planets orbiting close to it are likely destroyed. But more distant planets, asteroids, and comets can survive. Over time, some of this surviving debris falls inward toward the white dwarf, forming a thin disk of dust and gas. Astronomers have detected the chemical signatures of this debris in the atmospheres of white dwarfs, traces of silicon, iron, calcium, and even water. By studying these traces, scientists can learn about the composition of planets that orbited other stars, planets that no longer exist, broken apart by the gravitational tides of their dying parent star. There is something quietly moving about this. A white dwarf, the remnant of a star, slowly consuming the remnants of its own planets. A solar system eating itself, one atom at a time, over millions of years. One of the most remarkable white dwarfs ever discovered is BPM 37093, located approximately 50 light-years from Earth in the constellation Centaurus. This white dwarf has cooled to the point where its carbon interior has begun to crystallize, essentially turning into a diamond. Not a small diamond, a diamond roughly 4,000 kilometers in diameter, with an estimated mass of 5 million trillion pounds. Astronomers informally named it Lucy, after the Beatles' song Lucy in the Sky with Diamonds. It is, quite literally, a diamond the size of a planet, floating in the dark, slowly cooling toward eternity. The crystallization of white dwarfs is not unique to Lucy. As white dwarfs cool, their carbon and oxygen interiors gradually solidify from the center outward. This process releases a small amount of latent heat, which slightly slows the cooling rate. Observations from the European Space Agency's Gaia mission, which has cataloged the positions, motions, and properties of over 1 billion stars, have confirmed that many white dwarfs show signs of this crystallization process. In the data, there is a slight pileup of white dwarfs at a particular luminosity, a point where the release of latent heat temporarily pauses their cooling. This pileup is a direct signature of crystallization happening on a massive scale across the galaxy. Some white dwarfs spin rapidly. Others have powerful magnetic fields, sometimes millions of times stronger than Earth's. A few combine both traits, producing exotic phenomena that are still not fully understood. One such object is REJ 0317-853, a white dwarf with a magnetic field of roughly 340 million Gauss, compared to Earth's field of about 0.5 Gauss. The origin of such extreme magnetic fields in white dwarfs remains an active area of research. As of current estimates, there are roughly 10 billion white dwarfs in the Milky Way alone. They are everywhere, scattered throughout the galaxy like discarded embers from an ancient fire. Most are invisible to the naked eye. Most will never be observed by any telescope. They simply cool, quietly and patiently, in the dark. And they will continue to cool for a very, very long time. When a star sheds its outer layers on its way to becoming a white dwarf, those layers do not simply vanish. They expand outward into space, forming a glowing shell of gas known as a planetary nebula. The name is misleading. Planetary nebulae have nothing to do with planets. The term was coined in the 18th century by the astronomer William Herschel, who thought their rounded shapes resembled the disks of planets when viewed through early telescopes. The name stuck, even though we now know that these objects are the expelled atmospheres of dying stars. Planetary nebulae are among the most visually stunning objects in the universe. They come in an extraordinary variety of shapes: spheres, rings, butterflies, hourglasses, spirals. Some are perfectly symmetrical. Others are lopsided or multi-lobed. The shapes are determined by a combination of factors: the rotation of the original star, the presence of binary companions, magnetic fields, and the interaction of the ejected gas with the surrounding interstellar medium. The Ring Nebula, also known as Messier 57, is one of the most famous planetary nebulae. Located roughly 2,300 light-years from Earth in the constellation Lyra, it appears as a glowing ring of gas surrounding a tiny central star, the white dwarf that created it. The ring is about 1 light-year in diameter and is expanding at roughly 20 to 30 kilometers per second. Its colors, blue, green, red, correspond to different elements. Ionized oxygen glows blue-green, while nitrogen and hydrogen glow red. When you look at the Ring Nebula, you are seeing the last breath of a star, still expanding and glowing thousands of years after it was released. The Cat's Eye Nebula, designated NGC 6543, is even more complex. Located about 3,300 light-years away in the constellation Draco, it features a series of concentric shells, jets, and filaments that suggest the dying star ejected material in multiple pulses over thousands of years. The central star has a surface temperature of roughly 80,000 degrees Celsius, and its ultraviolet radiation illuminates the surrounding gas, causing it to fluoresce in vivid colors. The Hubble Space Telescope has captured images of the Cat's Eye that reveal an almost hypnotic level of detail. Nested bubbles within bubbles, each one a record of a separate ejection event. Not all planetary nebulae are delicate. The Helix Nebula, sometimes called the Eye of God, is one of the closest and largest planetary nebulae to Earth. Located approximately 700 light-years away in the constellation Aquarius. It spans roughly 5.7 light-years and appears, in deep exposures, as an enormous, luminous eye staring out of the darkness. Along its inner rim, thousands of small, dense knots of gas, called cometary knots because of their tadpole-like shapes, point away from the central star. Each of these knots is roughly the size of our solar system. They are being sculpted by the intense radiation from the white dwarf at the center, slowly evaporating over tens of thousands of years. The Butterfly Nebula, or NGC 6302, is among the most dramatic. Located about 3,800 light-years from Earth in the constellation Scorpius, it features 2 enormous lobes of gas expanding outward at speeds of over 600 kilometers per second. The central star is one of the hottest known, with a surface temperature estimated at around 250,000 degrees Celsius, more than 40 times the surface temperature of our Sun. Despite its brilliance, the central star is hidden behind a dense torus of dust, so it has never been directly observed in visible light. The butterfly shape is created because the expanding gas is channeled by this dusty ring, forced to flow outward along the poles rather than expanding equally in all directions. Planetary nebulae are transient. They last for only about 10,000 to 30,000 years, a blink in cosmic time before they disperse into the surrounding interstellar medium. The gas cools, thins, and eventually becomes indistinguishable from the general matter between the stars. But during their brief existence, they seed the galaxy with enriched material, elements forged in the cores of stars and then released back into space, where they will eventually be incorporated into new clouds of gas, new stars, and new planets. Every carbon atom in your body was once inside a star. Some of that carbon was released into space through the gentle exhalation of a planetary nebula, blown outward from a dying star billions of years ago, mixed into a cloud of gas, gathered by gravity into a new star and a new solar system, and eventually built into a molecule, a cell, and a living being. You are, in a very real and chemical sense, made of the remnants of stellar death. The Eskimo Nebula, NGC 2392, located about 6,500 light-years from Earth, has a particularly intriguing structure. It appears to have two shells, an inner bubble surrounded by a broader outer layer. The inner bubble was ejected roughly 10,000 years ago, while the outer material was released earlier in the star's red giant phase. The two shells interact, creating a complex and textured appearance. In January 2000, the Hubble Space Telescope captured an image of the Eskimo Nebula that became one of the most widely circulated astronomical photographs of that era. The Southern Ring Nebula, NGC 3132, gained new fame in July 2022 when it was one of the first objects imaged by the James Webb Space Telescope. The JWST's infrared cameras revealed details never seen before, including clear evidence that the central system contains at least two stars and possibly more. The dying star that produced the nebula had a companion whose gravitational influence helped shape the structure of the expanding gas. This discovery reinforced what astronomers had long suspected. Many planetary nebulae are shaped not by single stars dying alone, but by the complex gravitational interactions within binary or multiple star systems. Some planetary nebulae are almost perfectly circular, like Abell 39, a faint, ghostly bubble about 5 light-years in diameter and roughly 6,800 light-years from Earth. Its simplicity is itself a kind of beauty. A near-perfect sphere of glowing gas, expanding silently into the void, lit from within by a single white dwarf at its exact center. Others are startlingly irregular. The Red Spider Nebula, NGC 6537, features S-shaped waves of gas driven by stellar winds reaching speeds of 300 kilometers per second. The central star is one of the hottest in any known planetary nebula, and the resulting radiation sculpts the surrounding gas into complex, turbulent patterns. The duration of a planetary nebula's visibility depends on several factors: the density of the surrounding medium, the temperature of the central star, and the rate of expansion. But all of them fade eventually. The gas cools, the glow dims, and what remains is a white dwarf, alone in the dark, surrounded by nothing but the memory of what it once expelled. There is a gentle poetry in planetary nebulae. They are not violent, they are not destructive. They are simply the last act of a star that lived long enough to end quietly. A final exhalation, colored and luminous, before the long silence that follows. Not all stars die quietly. For the most massive stars in the universe, those born with 8 or more times the mass of our sun, death is not a gentle exhalation. It is an explosion of almost incomprehensible power. This is a supernova, and it is one of the most energetic events that can occur in the physical universe. A core collapse supernova begins in the final moments of a massive star's life. The star has spent millions of years fusing progressively heavier elements in its core. Hydrogen into helium, helium into carbon, carbon into neon, neon into oxygen, oxygen into silicon, and finally silicon into iron. Each stage releases less energy than the last, and each stage lasts for a shorter time. The silicon burning phase, the final stage, may last only a single day. When the core fills with iron, fusion stops. Iron is the most tightly bound nucleus in nature, and fusing it further does not release energy. It absorbs it. In that instant, the star loses the outward pressure that has supported it against gravity for its entire life. The core collapses, not slowly, not gradually. The collapse happens in about a quarter of a second. The inner core, roughly the mass of our sun, shrinks from a sphere thousands of kilometers wide to a ball just 20 kilometers across. The density reached during this collapse is extraordinary. The material in the collapsing core is compressed so violently that protons and electrons are forced together to form neutrons. The core becomes an almost solid ball of neutrons, a proto-neutron star. The collapse is halted not by any chemical or thermal pressure, but by the nuclear strong force and neutron degeneracy pressure, quantum mechanical effects that resist the compression of neutrons beyond a certain point. The outer layers of the star, still falling inward at a significant fraction of the speed of light, slam into this suddenly rigid core and bounce. The result is a shock wave that propagates outward through the star, tearing it apart from the inside out. This shock wave is aided by a flood of neutrinos, ghostly particles produced in enormous quantities during the collapse, which carry away energy and help push the outer layers outward. The explosion that follows is staggeringly luminous. A single supernova can briefly outshine an entire galaxy, hundreds of billions of stars combined. The energy released is roughly 10 to the power of 44 joules, a number so large it essentially loses meaning without comparison. More energy is released in the few seconds of a core collapse supernova than our sun will emit in its entire 10 billion year lifetime. The light from a supernova can be visible across millions of light years. Throughout history, humans have witnessed supernovae in our own galaxy with the naked eye. In 1054 AD, Chinese astronomers recorded a guest star that appeared in the constellation Taurus and was bright enough to be visible during the day for 23 days. The remnant of that explosion is still visible today. It is the Crab Nebula, one of the most studied objects in all of astronomy. In 1572, the Danish astronomer Tycho Brahe observed a supernova in the constellation Cassiopeia. He was so struck by the sight of a new star appearing where none had been before that he wrote an entire book about it. The event challenged the prevailing Aristotelian belief that the heavens were unchanging and perfect. In 1604, Johannes Kepler observed another supernova, also in our galaxy. It was the last supernova visible to the naked eye in the Milky Way. More than 400 years have passed since then, and no galactic supernova has been seen since. Statistically, the Milky Way should produce a supernova roughly once every 50 to 100 years, which means we are, in a sense, overdue. But predicting exactly when and where the next one will occur is beyond current capabilities. The most recent nearby supernova occurred in 1987, not in the Milky Way itself, but in the Large Magellanic Cloud, a small satellite galaxy roughly 168,000 light-years away. Designated SN 1987A, it was the first supernova visible to the naked eye since Kepler's. It was also the first supernova from which neutrinos were detected, a burst of roughly 25 neutrinos captured by detectors on Earth, arriving just hours before the visible light. Those 25 particles confirmed decades of theoretical predictions about how core collapse supernovae work. The material ejected by a supernova expands outward at thousands of kilometers per second, forming what is known as a supernova remnant. These remnants are vast, expanding shells and filaments of superheated gas enriched with heavy elements forged in the explosion itself. Gold, platinum, uranium. Many of the heaviest elements on the periodic table are created not inside stars, but in the extreme conditions of a supernova explosion, through a process called rapid neutron capture, or the R process. The Crab Nebula, the remnant of the 1054 supernova, is about 11 light-years across and is still expanding at roughly 1,500 kilometers per second. At its center lies a pulsar, a rapidly spinning neutron star that rotates about 30 times per second, sending beams of radiation sweeping across the cosmos. The energy from this pulsar powers the nebula's eerie glow, making the Crab Nebula one of the strongest sources of radiation in the sky across nearly every wavelength. Cassiopeia A, the remnant of a supernova that likely occurred around 1680 AD, but was not widely recorded, is one of the brightest radio sources in the sky. It is roughly 10 light-years across and expanding at about 4,000 to 6,000 kilometers per second. Observations from the Chandra X-ray Observatory have revealed the presence of heavy elements scattered throughout the remnant: silicon, sulfur, calcium, iron, arranged in patterns that tell the story of the explosion itself. The Vela supernova remnant, located about 800 light-years from Earth, is the remains of a supernova that occurred roughly 11,000 to 12,300 years ago. It is enormous, spanning about 8 degrees on the sky, or roughly 16 times the apparent diameter of the full moon. At its center is the Vela pulsar, spinning about 11 times per second. Supernova remnants do not last forever. Over tens of thousands of years, they expand, cool, and eventually merge with the surrounding interstellar medium. But in doing so, they enrich that medium with heavy elements, compress nearby clouds of gas, and sometimes trigger the formation of new stars. The shock waves from supernovae are one of the primary mechanisms by which star formation is propagated across a galaxy. Death, in this context, directly causes birth. There is evidence that a nearby supernova may have influenced life on Earth. In the ocean floor, scientists have found traces of iron-60, a radioactive isotope of iron not produced naturally on Earth, in geological layers dating to roughly 2.6 million years ago, and again at about 6 million years ago. This iron-60 is believed to have been deposited by the debris from one or more nearby supernova, perhaps 100 to 300 light-years away. Whether these events influenced evolution or climate in any significant way remains uncertain, but the chemical fingerprint is there, a trace of stellar death embedded in the Earth itself. The energy budget of a supernova is dominated not by light, but by neutrinos. Approximately 99% of the energy released in a core collapse supernova is carried away by neutrinos. Roughly 3 times 10 to the power of 46 joules worth of these particles flood outward in a burst lasting only about 10 seconds. The visible light, as spectacular as it is, represents only about 1% of the total energy. The shock wave that destroys the star carries about 1% as well. The rest is carried silently, invisibly, by neutrinos that pass through the outer layers of the star, through any surrounding planets, and out into the universe, interacting with almost nothing. If a supernova were to occur at the distance of the nearest star, about 4 light-years away, the neutrino flux would be so intense that even neutrinos, which barely interact with matter at all, would deliver a lethal radiation dose. Fortunately, no massive star capable of producing a supernova exists anywhere near that close to us. Supernovae are not just endings. They are the universe's most dramatic acts of recycling. Everything that was once locked inside a massive star, the carbon, the oxygen, the silicon, the iron, the gold, the uranium, is scattered back into the cosmos, ready to be gathered again by gravity into new stars, new planets, and perhaps new life. The iron in your blood, the calcium in your bones, the oxygen in your lungs, Much of it was forged in the cores of massive stars and released into space by the violence of their deaths. There is a strange tenderness in this. The most destructive events in the universe are also among the most creative. Without supernovae, the universe would contain only hydrogen, helium, and trace amounts of lithium, the elements produced in the Big Bang. There would be no carbon, no oxygen, no silicon, no iron, no rocky planets, no water, no life. Everything complex, everything structured, everything that you are owes its existence to the death of a star. After a core collapse supernova, if the remaining core has a mass between roughly 1.4 and 3 times the mass of our Sun, the result is a neutron star. These are among the most extreme objects in the known universe. Objects so dense, so compact, and so strange that they stretch the limits of what physics can describe. A typical neutron star has a mass of about 1.4 to 2 times the mass of our Sun, compressed into a sphere roughly 20 kilometers in diameter. To put that in perspective, that is roughly the size of a city. Imagine the entire mass of the Sun, 330,000 times the mass of Earth, squeezed into a ball that would fit comfortably within the boundaries of a mid-sized town. The density of the material inside a neutron star is roughly 1 billion tons per cubic centimeter. A sugar cube-sized sample of neutron star matter, if you could somehow transport it to Earth, would weigh approximately 1 billion tons, roughly the weight of every car on Earth combined. The name neutron star comes from the composition of its interior. During the collapse that forms a neutron star, the protons and electrons in the core are crushed together by gravity, and they merge through a process called inverse beta decay to form neutrons. The resulting object is composed almost entirely of neutrons, uncharged particles that are normally found inside atomic nuclei. In a neutron star, there are no atoms, no molecules, no chemistry, just an incomprehensibly dense sea of neutrons held together by gravity and supported against further collapse by neutron degeneracy pressure and the repulsive component of the nuclear strong force. The surface gravity of a neutron star is roughly 200 billion times the surface gravity of Earth. If you could stand on the surface of a neutron star, which you cannot, because you would be instantly compressed into a thin layer of matter, you would weigh about 15 trillion kilograms. Dropping an object from a height of 1 meter would result in it hitting the surface at roughly 7.2 million kilometers per hour. The surface is so gravitationally intense that light itself is visibly bent. You could, in theory, see the back of the neutron star by looking past its edges because light curves around it. The surface of a neutron star is thought to consist of a thin crust of iron nuclei arranged in a crystalline lattice, essentially a shell of solid iron about 1 to 2 kilometers thick. Beneath this crust lies a region of increasingly neutron-rich nuclei, and deeper still, a fluid interior of free neutrons with a small fraction of protons and electrons. At the very center, the density is so extreme that the nature of matter is genuinely unknown. Some theories suggest the core may contain exotic states of matter, quark-gluon plasma, strange quark matter, or other phases that have never been observed in any laboratory on Earth. Neutron stars rotate rapidly. This is a consequence of conservation of angular momentum, the same principle that makes a figure skater spin faster when they pull in their arms. The original star may have been rotating slowly, perhaps once every few weeks. But when the core collapses from thousands of kilometers to just 20, the rotation speed increases dramatically. A newly formed neutron star can spin hundreds of times per second. The fastest spinning neutron star known is PSRJ 1748-2446 AD, located in the globular cluster Terzan 5, roughly 18,000 light-years from Earth. It rotates 716 times per second. This means that a point on its equator is moving at roughly 24% of the speed of light. The forces involved at such rotational speeds are immense. If the neutron star were any less dense, it would tear itself apart. Neutron stars also have extraordinarily powerful magnetic fields. A typical neutron star has a magnetic field roughly 1 trillion times stronger than Earth's. These magnetic fields are a relic of the original star's field, compressed and amplified during the collapse. The magnetic field channels charge particles along its lines, producing beams of radiation that emanate from the magnetic poles. When a neutron star cools, it can develop a phenomenon known as a starquake. The solid crust, stressed by the changes in the star's rotation rate and the shifting of material beneath it, can crack, much like the crust of the Earth cracks during an earthquake. But because the crust of a neutron star is incredibly strong, held together by nuclear forces rather than the chemical bonds that hold terrestrial rocks together, these quakes release enormous amounts of energy. A single starquake can release more energy than our sun emits in months. The interiors of neutron stars may contain superfluid and superconducting matter. At the temperatures and densities found inside a neutron star, neutrons can pair up and form a superfluid, a state of matter with zero viscosity that flows without any friction. Similarly, the small number of protons inside the star can pair up and become superconducting, carrying electrical current without resistance. These quantum states of matter, which on Earth can only be produced at temperatures near absolute zero, exist naturally inside neutron stars at temperatures of millions of degrees, a seeming paradox that arises from the extreme density. Observations have provided indirect evidence for superfluidity in neutron stars. In 2011, a study of the neutron star in the Cassiopeia A supernova remnant showed that it was cooling more rapidly than standard models predicted. The best explanation was that the neutrons in its core had recently transitioned into a superfluid state, which changed the rate at which neutrinos could carry heat away from the interior. Neutron stars are sometimes found in binary systems, orbiting another star or even another neutron star. In 1974, astronomers Russell Hulse and Joseph Taylor discovered the first binary neutron star system, PSRB 1913 plus 16, also known as the Hulse-Taylor binary. By precisely timing the pulsar's signals over many years, they were able to measure the orbital decay of the system. The two neutron stars were slowly spiraling toward each other, losing energy in exactly the way predicted by Einstein's general theory of relativity through the emission of gravitational waves. This discovery provided the first indirect evidence for gravitational waves, and Hulse and Taylor were awarded the Nobel Prize in Physics in 1993. When two neutron stars finally merge, the result is a cataclysmic event called a kilonova. On August 17, 2017, the LIGO and Virgo gravitational wave detectors observed the gravitational waves from a neutron star merger, designated GW 170817, located roughly 130 million light-years away. This was the first time gravitational waves from a neutron star merger had been detected, and it was also observed across the electromagnetic spectrum, in gamma rays, X-rays, ultraviolet, visible light, infrared, and radio waves. The merger produced enormous quantities of heavy elements, including gold and platinum, confirming that neutron star mergers are a major source of the heaviest elements in the universe. The amount of gold produced in a single neutron star merger has been estimated at several times the mass of Earth. The platinum produced is similarly vast. These elements are scattered into space by the explosion, eventually mixing with the interstellar medium and being incorporated into new stars and planets. The gold in your ring the platinum in a catalytic converter. Some of it may have been forged in the collision of two neutron stars billions of years ago in a galaxy far from here. There is something extraordinary about the idea that the densest objects in the universe, when they collide, produce the rarest and most precious elements we know. That gold, a symbol of wealth and beauty throughout human history, is born from the most violent gravitational events in the cosmos. The universe does not waste anything. Even destruction is a form of creation. Among the most remarkable things a dead star can do is send messages across the galaxy. Not deliberately, not with intent, but with a precision so extraordinary that when humans first detected these signals, they seriously considered the possibility that they had been sent by an intelligent civilization. A pulsar is a neutron star that emits beams of electromagnetic radiation from its magnetic poles. As the neutron star rotates, these beams sweep across space like the beams of a lighthouse. If Earth happens to lie in the path of one of these beams, we detect a regular pulse of radiation, a flash that repeats with astonishing consistency. Some pulsars flash once every few seconds, others flash hundreds of times per second, and the timing of these flashes is so precise that pulsars are among the most accurate clocks in the universe. The first pulsar was discovered in November 1967 by Jocelyn Bell Burnell and Anthony Hewish at the Mullard Radio Astronomy Observatory in Cambridge, England. Bell Burnell, then a graduate student, noticed a peculiar signal in the data from a radio telescope, a series of regular pulses repeating every 1.337 seconds. The signal was so regular and so unexpected that the researchers initially designated it LGM1, standing for Little Green Men, a half-serious nod to the possibility that the signal might be artificial. It was not. It was the first pulsar ever detected, now designated PSRB 1919+21. The discovery was transformative. It confirmed the existence of neutron stars, which had been predicted theoretically but never directly observed. It opened an entirely new field of astrophysics, and it remains one of the most significant discoveries in the history of radio astronomy. Hewish received the Nobel Prize in Physics in 1974 for the discovery, though the omission of Bell Burnell from the prize has been widely regarded as one of the greatest oversights in the history of the Nobel. The mechanism that produces pulsar beams is related to the neutron star's magnetic field. As the star rotates, its powerful magnetic field accelerates charged particles near the magnetic poles. These accelerated particles emit radiation in a narrow beam along the magnetic axis. Because the magnetic axis is typically tilted relative to the rotational axis, the beams sweep through space as the star turns, creating the pulsing effect observed from Earth. The rotation rates of pulsars span an enormous range. The Crab pulsar, at the heart of the Crab Nebula, rotates about 30 times per second. This is considered relatively slow for a pulsar, though it is far faster than any macroscopic object in everyday experience. At the other end of the spectrum are the millisecond pulsars, neutron stars that have been spun up to extraordinary speeds by accreting matter from a binary companion. The fastest known millisecond pulsar, PSRJ 1748-2446 AD, completes 716 rotations every second. At that speed, the star's equator is moving at roughly 70,000 kilometers per second. Millisecond pulsars are extraordinarily stable timekeepers. The regularity of their pulses is comparable to, and in some cases exceeds, the precision of atomic clocks. This makes them valuable tools for fundamental physics. Arrays of millisecond pulsars are being used in projects like the North American Nanohertz Observatory for gravitational waves, or nanograv, to detect the background hum of gravitational waves that permeates the universe. By monitoring tiny variations in the arrival times of pulsar signals at Earth, researchers can detect the stretching and compressing of space-time caused by gravitational waves from distant sources. Merging supermassive black holes, for instance, orbiting each other at the centers of colliding galaxies. In June 2023, Nanograv announced evidence for the existence of this gravitational wave background, a low-frequency hum of space-time vibrations generated by the combined effect of countless supermassive black hole binaries across the universe. The detection was made possible by 15 years of precise pulsar timing observations. Dead stars, it turns out, can be used to listen to the echoes of other cosmic events happening billions of light years away. Some pulsars exhibit a phenomenon called glitching, sudden, tiny increases in their rotation rate. These glitches are thought to be caused by the transfer of angular momentum from the superfluid interior of the neutron star to its solid crust. As the star gradually slows down due to the emission of radiation, the superfluid interior, which rotates independently, can suddenly transfer its excess spin to the crust, causing a detectable speed-up. The Vela pulsar is one of the best-studied glitching pulsars, having experienced numerous glitches since its discovery. Pulsars slow down over time. As they emit radiation and lose rotational energy, their spin period gradually increases. A pulsar that spins 30 times per second today will spin more slowly 1,000,000 years from now and more slowly still 1,000,000,000 years hence. Eventually, the pulsar's rotation will slow to the point where its magnetic field can no longer accelerate particles to produce detectable radiation. The pulsar switches off. It becomes a silent neutron star, still there, still dense, still spinning, but no longer visible as a pulsar. This is sometimes called the pulsar death line, the boundary beyond which a neutron star's rotation is too slow to power its emission mechanism. The Milky Way is estimated to contain roughly 100 million neutron stars, but only a small fraction of these are currently visible as pulsars. Most have either slowed beyond the death line, or their beams do not sweep across Earth. As of current surveys, roughly 3,000 pulsars have been detected in our galaxy. Each one is a dead star, still spinning, still sending signals across the void, like a lighthouse left running long after the harbor it once served has crumbled into the sea. Perhaps the most extraordinary use of pulsars is as cosmic navigation beacons. In 1972 and 1973, NASA launched the Pioneer 10 and Pioneer 11 spacecraft, each carrying a gold-plated plaque designed to communicate the origin of the craft to any extraterrestrial civilization that might encounter it. On the plaque is a diagram showing the position of our Sun relative to 14 pulsars, identified by their unique pulse periods and directions. The idea was that pulsars, with their distinctive timing signatures, could serve as a kind of cosmic address system, a way for any technologically advanced civilization to locate our solar system within the galaxy. The same pulsar map appears on the Voyager Golden Record, launched in 1977. It is, in a sense, a map drawn in the light of dead stars. And those dead stars, should anyone ever find the record, will still be spinning, perhaps for billions of years to come. Pulsars have also confirmed some of the strangest predictions of general relativity. The double pulsar system, PSRJ 0737-3039, discovered in 2003, consists of two neutron stars, both of which are visible as pulsars, orbiting each other every 2.4 hours. This system has allowed physicists to test general relativity with unprecedented precision, measuring effects like the Shapiro time delay, geodetic precession, and orbital decay due to gravitational wave emission. Every prediction of Einstein's theory has been confirmed to extraordinary accuracy. dead stars, still turning in the dark, have become the most precise laboratories for testing the fabric of space-time itself. There is something almost poetic about pulsars, a star that has died, that has collapsed under the weight of its own gravity, that has shed its outer layers in a cataclysmic explosion, and yet it is not silent. It spins, it sends signals, it speaks across light years, across millennia, with a regularity so precise it can be used to test the nature of reality itself. Even in death, a star can be remarkably eloquent. Among the neutron stars, there is a class so extreme that they deserve their own category. These are the magnetars, neutron stars with magnetic fields so unimaginably powerful that they represent the strongest magnets in the known universe. A magnetar's magnetic field is typically on the order of 10 to the power of 14 to 10 to the power of 15 Gauss. To put this in perspective, the Earth's magnetic field is about 0.5 Gauss. A refrigerator magnet produces about 50 Gauss. A medical MRI machine generates roughly 10,000 to 30,000 Gauss. A typical neutron star has a magnetic field of about 1 trillion Gauss. And a magnetar has a field 1,000 times stronger than that, roughly 1 quadrillion Gauss. At these field strengths, matter behaves in ways that have no analogy in everyday experience. The magnetic field of a magnetar is strong enough to distort the shapes of atoms, stretching them into long, thin cylinders aligned with the field lines. A human body brought within 1,000 kilometers of a magnetar would be torn apart, not by gravity, but by the magnetic field itself, which would disrupt the chemistry of every molecule in the body. At closer range, the field is strong enough to affect the vacuum of empty space, creating a phenomenon known as vacuum birefringence, in which the vacuum itself becomes optically active, bending and splitting light like a crystal. Magnetars were first proposed theoretically in 1992 by astrophysicists Robert Duncan and Christopher Thompson. They suggested that a specific subset of neutron stars could develop ultra-strong magnetic fields during their formation, powered by a vigorous convective dynamo in the first seconds after the supernova collapse. If the proto-neutron star is hot enough and convecting rapidly enough, the dynamo can amplify the magnetic field to magnetar levels, far beyond what a simple compression of the original star's field would produce. The existence of magnetars was confirmed observationally through their dramatic outbursts. Magnetars are the source of 2 types of extreme high-energy phenomena: soft gamma repeaters, SGRs, and anomalous X-ray pulsars, AX pulses. Both emit bursts of X-rays and gamma rays powered not by rotation, as in ordinary pulsars, but by the decay and rearrangement of their colossal magnetic fields. The most famous magnetar event occurred on December 27, 2004, when a magnetar designated SGR 1806-20, located about 50,000 light-years away on the far side of the Milky Way, produced the brightest flash of energy ever detected from outside our solar system. The giant flare lasted only about 1/10 of a second at its peak, but during that brief instant, it released more energy than our sun emits in 250,000 years. The flash was so intense that it measurably disturbed Earth's ionosphere, even though the source was halfway across the galaxy. Had the magnetar been located just 10 light-years from Earth, the radiation would have been catastrophic for life on our planet. The flare was caused by a catastrophic rearrangement of the magnetar's magnetic field, essentially a starquake of extraordinary magnitude. The crust of the magnetar cracked, and the magnetic field lines, twisted and stressed beyond their breaking point, snapped and reconnected in a sudden release of stored energy. The event demonstrated that magnetars are not just extreme, they are unstable. Their own magnetic fields are a source of continual stress, and the energy stored in those fields can be released suddenly and violently. Only about 30 magnetars have been identified in the Milky Way and the Magellanic Clouds as of current surveys. They are rare, far rarer than ordinary pulsars. This is partly because the conditions required to produce a magnetar during a supernova are uncommon, and partly because magnetars have short, active lifetimes. Their magnetic fields decay over roughly 10,000 years, after which the magnetar settles down into a more ordinary, quieter neutron star. This means that the magnetars we observe today are all relatively young, born within the last 10,000 to 20,000 years. During their brief active phase, magnetars are among the most violent objects in the cosmos. They emit bursts of X-rays and gamma rays at irregular intervals, sometimes quiet for months, and then erupting in a flurry of activity. Some bursts are small, brief flickers of X-ray emission lasting fractions of a second. Others are giant flares like the one from SGR 1806-20, capable of being detected across the galaxy. The magnetic field of a magnetar affects not just matter, but space itself. According to quantum electrodynamics, extremely strong magnetic fields can polarize the vacuum, changing the way light propagates through what would otherwise be empty space. In 2017, astronomers using the European Southern Observatory's Very Large Telescope reported the first observational evidence for vacuum birefringence around a neutron star, RxJ 185-6.5-3754, located about 400 light-years from Earth. While this particular neutron star may not be a full magnetar, the observation confirmed a prediction made by Werner Heisenberg and Hans Euler in 1936 and demonstrated that the vacuum of space is not truly empty. It can be polarized, twisted, and shaped by sufficiently strong fields. Magnetars may also be responsible for some of the mysterious fast radio bursts, brief, intense pulses of radio emission that last only milliseconds but release enormous amounts of energy. In April 2020, a magnetar in our own galaxy, SGR 1935+2-154, produced a burst of radio waves that was remarkably similar in character to the extragalactic, fast radio bursts that had been puzzling astronomers for years. This was the first time a fast radio burst was clearly linked to a known source, and it strongly suggested that at least some fast radio bursts are produced by magnetars. The interiors of magnetars remain deeply mysterious. The extreme magnetic fields are expected to have profound effects on the superdense matter within, potentially affecting the behavior of the superfluid neutrons, the superconducting protons, and any exotic matter that might exist in the core. Some theorists have speculated that the cores of magnetars might contain quark matter, a state in which the individual quarks that make up neutrons and protons are no longer confined within those particles, but instead roam freely in a quark-gluon plasma. If true, magnetars would contain a state of matter that has not existed freely in the universe since the first microseconds after the Big Bang. There is a strange beauty in magnetars. They are objects of such extremity that they bend not just light and matter, but the very fabric of empty space. They are rare, violent, and brief, burning through their magnetic energy in a few thousand years and then fading into quieter obscurity. They are the most tempestuous residents of the stellar graveyard, and even in a universe filled with extreme objects, they stand apart. Beyond the neutron star, there is only one destination left for a collapsing stellar core. If the remnant mass exceeds roughly 3 times the mass of our Sun, a boundary known as the Tolman-Oppenheimer-Volkoff limit, then no known force in physics can prevent further collapse. The matter falls inward, past the point of neutron degeneracy pressure, past the point of quark matter, past every threshold physics can describe, and becomes a black hole. A black hole is, in the simplest terms, a region of space-time where gravity is so intense that nothing can escape. Not matter, not light, not information. The boundary that separates the interior of a black hole from the rest of the universe is called the event horizon. It is not a physical surface. There is no wall, no membrane, no barrier you could touch. The event horizon is simply the distance from the center at which the escape velocity equals the speed of light. Anything that crosses this boundary, any particle, any photon, any signal of any kind, is lost to the outside universe forever. The idea of a dark object whose gravity prevented the escape of light was first proposed in the 18th century by the English clergyman John Michel in 1783, and independently by the French mathematician Pierre-Simon Laplace in 1796. But the modern understanding of black holes comes from Albert Einstein's general theory of relativity, published in 1915. In 1916, the German physicist Karl Schwarzschild found the first exact solution to Einstein's field equations, describing the space-time around a non-rotating, spherically symmetric mass. The Schwarzschild solution predicted the existence of a critical radius, now called the Schwarzschild radius, within which nothing could escape. For an object with the mass of our Sun, this radius is about 3 kilometers. For an object with the mass of Earth, it would be about 9 millimeters. For decades, black holes were considered mathematical curiosities, solutions to the equations, but not necessarily real objects in the universe. It was not until the mid-20th century that physicists began to take them seriously as physical entities. The work of Roger Penrose in the 1960s showed that black hole formation was an inevitable consequence of general relativity under certain conditions. Specifically, that the collapse of a sufficiently massive star must lead to a singularity, a point of infinite density at the center of the black hole. Penrose was awarded the Nobel Prize in Physics in 2020 for this work. The singularity at the center of a black hole is, in a sense, the ultimate graveyard. It is where the matter that formed the star ends up, compressed to infinite density, occupying zero volume. At least, that is what general relativity predicts. Most physicists believe that the singularity is not a literal reality, but rather a sign that general relativity breaks down at extreme scales and must be replaced by a quantum theory of gravity, a theory that does not yet exist. What actually happens at the center of a black hole remains one of the deepest unsolved problems in physics. Stellar mass black holes, the ones formed by the deaths of massive stars, typically have masses ranging from about 5 to 100 times the mass of our Sun. They are small by astronomical standards. A black hole with 10 times the Sun's mass would have a Schwarzschild radius of about 30 kilometers. That's smaller than many cities. But within that tiny volume lies an object whose gravitational influence can shape the behavior of matter and light across vast distances. One of the most well-studied stellar black holes is Cygnus X1, located about 6,000 light-years from Earth in the constellation Cygnus. It was one of the first objects widely accepted as a black hole, following observations in the 1970s that revealed a compact object with a mass too large to be a neutron star, accreting matter from a blue supergiant companion star. The infouling material forms an accretion disk, a swirling, superheated disk of gas spiraling inward toward the event horizon. As the gas in the accretion disk is compressed and heated to millions of degrees, it emits intense X-ray radiation, making Cygnus X one of the strongest X-ray sources in the sky. Accretion disks are how we detect most stellar black holes. The black hole itself emits nothing. By definition, nothing can escape its event horizon. But the material falling toward the black hole, heated to extreme temperatures by friction and compression, radiates brilliantly before it crosses the event horizon. In some cases, powerful jets of high-energy particles are launched from the vicinity of the black hole, perpendicular to the accretion disk, at speeds approaching the speed of light. The exact mechanism that produces these jets is not fully understood, but it is believed to involve the interaction of the accretion disk with the black hole's spin and magnetic fields. The mass of a stellar black hole can be measured by observing its gravitational effects on nearby objects. In binary systems, where a black hole orbits with a companion star, the orbital parameters reveal the masses of both objects. In cases where no companion is present, black holes can be detected through gravitational microlensing, the bending of light from more distant stars as the black hole passes between them and Earth. In 2022, astronomers using data from the Hubble Space Telescope reported the first definitive detection of an isolated, free-floating black hole, OGLE 2011 BLG 0462, a stellar mass black hole roughly 7 times the mass of the Sun, wandering alone through the galaxy about 5,000 light-years from Earth. It was detected through the subtle bending and magnification of background starlight as the black hole drifted in front of it. The Milky Way alone is estimated to contain roughly 100 million stellar mass black holes. Most of them are completely dark, no companion star, no accretion disk, no jets. They drift silently through the galaxy, interacting with almost nothing, invisible except through their gravitational effects. They are the quietest residents of the stellar graveyard. Not embers, not spinning lighthouses, not magnetic storms, just deep, patient, permanent curves in the fabric of space-time. When a star crosses too close to a black hole, it can be torn apart by tidal forces, the difference in gravitational pull between the near side and far side of the star. This is called a tidal disruption event, and it produces a spectacular flare of radiation as the stellar material spirals into the black hole. Several tidal disruption events have been observed in other galaxies, each one a momentary illumination of a black hole that was otherwise completely invisible. Near the event horizon, time itself behaves strangely. According to general relativity, time passes more slowly in stronger gravitational fields. An observer falling toward a black hole would not notice anything unusual. From their perspective, time would seem to flow normally. But to a distant observer watching from far away, the falling object would appear to slow down as it approached the event horizon. It would never appear to cross it. Instead, it would seem to hover at the boundary, growing dimmer and redder as the light it emits is stretched to longer wavelengths by the increasing gravitational redshift. In a sense, a black hole accumulates the images of everything that has ever fallen into it, frozen on the surface of the event horizon for eternity, at least from the perspective of the outside universe. Black holes are not eternal. In 1974, Stephen Hawking proposed that black holes can slowly lose mass through a quantum mechanical process now known as Hawking radiation. Near the event horizon, the intense gravitational field can cause the spontaneous creation of particle-antiparticle pairs from the vacuum. Normally, these pairs would annihilate each other almost instantly, but if one particle falls into the black hole while the other escapes, the black hole loses a tiny amount of mass. Over extraordinarily long timescales, this process causes the black hole to slowly evaporate. For stellar mass black holes, this evaporation is inconceivably slow. A black hole with 10 times the mass of our Sun would take roughly 10 to the power of 68 years to evaporate, a number so large that it makes the current age of the universe About 13.8 billion years seem like less than an instant. But eventually, given enough time, even black holes will vanish. In the final moments of evaporation, the black hole would shrink rapidly and release a burst of radiation, a kind of final farewell before it ceases to exist entirely. Black holes challenge our understanding of physics in ways that few other objects can. The information paradox, the question of what happens to the information contained in the matter that falls into a black hole, has been one of the central puzzles of theoretical physics for half a century. General relativity says the information is lost behind the event horizon. Quantum mechanics says information cannot be destroyed. The tension between these two pillars of modern physics remains unresolved, and its resolution may require a fundamentally new understanding of the nature of space, time, and reality. There is something strangely compelling about black holes. They are the ultimate expression of gravity's power. Objects that represent the complete victory of gravity over every other force in nature. They are where matter goes when it has nowhere else to go. They are the final stop in the stellar graveyard and the most permanent. While white dwarfs cool and neutron stars slow, black holes simply persist, warping space-time, drifting silently, waiting with infinite patience for the universe to grow old around them. When a star explodes as a supernova, the explosion itself is brief, a few seconds for the core collapse, a few weeks for the peak brightness. But the aftermath lasts for thousands of years. The material ejected by the explosion expands outward into space at tremendous speeds, sweeping up the surrounding interstellar medium and creating vast, luminous structures called supernova remnants. These are the tombs of dead stars. Not quiet and contained, but enormous, chaotic, and still evolving. Supernova remnants pass through several distinct phases as they expand. In the first phase, called free expansion, the ejected material plows through the surrounding medium at speeds of thousands of kilometers per second, encountering relatively little resistance. The remnant grows rapidly, and the ejected material retains its original velocity and structure. After several hundred years, the remnant enters the Sedov-Taylor phase, in which the swept-up interstellar material begins to dominate the dynamics. The expansion slows, and a strong shock wave forms at the leading edge of the remnant, heating the surrounding gas to millions of degrees. This hot gas emits X-rays, making supernova remnants prominent X-ray sources. Over thousands of years, the remnant continues to expand and cool, entering the snowplow phase, in which the shell of swept-up material becomes dense and the interior cools. Eventually, after tens of thousands to hundreds of thousands of years, the remnant disperses into the interstellar medium, its identity lost, its material mixed with the general gas and dust between the stars. The Cygnus Loop, also known as the Veil Nebula, is one of the most beautiful supernova remnants visible from Earth. Located about 2,400 light-years away in the constellation Cygnus, it is the remnant of a supernova that occurred roughly 10,000 to 20,000 years ago. The remnant is enormous, spanning about 3 degrees on the sky, or roughly 6 times the apparent diameter of the full moon. In long exposure photographs, it appears as delicate filaments of glowing gas, twisted and folded like cosmic drapery, colored blue, green, and red by the emissions of different elements. The filamentary structure of the Cygnus Loop is created by the interaction of the expanding shockwave with irregularities in the surrounding interstellar medium. Where the shock encounters denser clumps of gas, it is slowed and deformed, creating the intricate patterns visible in images. The colors correspond to different elements. Oxygen emits blue-green light, hydrogen emits red, and sulfur emits deep red. Tycho's supernova remnant, the remains of the supernova observed by Tycho Brahe in 1572, is still expanding roughly 450 years later. Observations from the Chandra X-ray Observatory have revealed a nearly spherical shell of hot gas with the outermost shock wave moving at roughly 5,000 kilometers per second. Inside the shell, the distribution of elements, silicon, sulfur, iron, tells the story of the thermonuclear explosion that produced it. Tycho's remnant is classified as a Type 1a supernova remnant, meaning it was produced by the detonation of a white dwarf rather than the collapse of a massive star. Kepler's supernova remnant from the 1604 event is located roughly 20,000 light-years away. It is smaller and fainter than Tycho's remnant, but has been studied extensively in X-rays, infrared, and radio wavelengths. The remnant shows an asymmetric structure, suggesting that the explosion occurred in a complex environment, possibly within a dense circumstellar medium produced by the progenitor star or its companion before the explosion. The remnant of SN 1987A, the supernova in the Large Magellanic Cloud, has been observed continuously since the explosion and provides a unique opportunity to watch a supernova remnant evolve in real time. In the years following the explosion, the Hubble Space Telescope captured images showing a ring of gas surrounding the explosion site, material that had been ejected by the progenitor star thousands of years before the supernova itself. As the expanding debris from the explosion reached this ring, it began to light up, producing a string of bright spots around the ring's circumference. These hot spots have grown brighter and more numerous over the decades, and the remnant continues to evolve. In 2024, the James Webb Space Telescope observed SN 1987A in infrared wavelengths, revealing new details about the structure of the inner debris and the possible presence of a compact object at the center, either a neutron star or a black hole. The nature of this central remnant has been debated since the supernova occurred, and the JWST observations may help resolve the question. Supernova remnants are among the most important objects in the galaxy for the cycle of matter. The heavy elements they scatter, carbon, oxygen, silicon, iron, gold, platinum, uranium, are the raw materials for planets, moons, asteroids, comets, and ultimately life. The calcium in bones, the iron in blood, the carbon in DNA. All of it was processed through the interior of a massive star and scattered by the violence of its death. Supernova remnants also play a role in accelerating cosmic rays, high-energy particles that travel through the galaxy at nearly the speed of light. The shock waves at the edges of supernova remnants can accelerate protons and atomic nuclei to extraordinary energies through a process called diffusive shock acceleration. These cosmic rays pervade the galaxy, and some of them strike Earth's atmosphere, producing showers of secondary particles that reach the ground. Every second, roughly 10,000 cosmic rays pass through your body. Some of them were accelerated by the expanding tomb of a dead star, thousands of years ago and thousands of light years away. There is a vastness to supernova remnants that is hard to convey. The Cygnus loop is roughly 120 light years across, a shell of glowing gas large enough to contain thousands of solar systems. Cassiopeia A is 10 light years across and expanding rapidly. The Vela remnant is even larger. These are not small monuments. They are continent-sized memorials, visible across the galaxy, slowly fading but enduring for millennia. And inside each one, at the center, lies the remnant of the star itself, a neutron star, a pulsar, a magnetar, or a black hole. The tomb surrounds the body, the explosion marks the grave, and the enriched material, scattered across light years, becomes the inheritance left behind for the next generation of stars. Stars do not always die alone. In the Milky Way, Roughly half of all star systems are binaries, pairs of stars orbiting each other, bound together by gravity. When one star in a binary system dies before the other, the interaction between the dead remnant and its living companion can produce some of the most spectacular and strange phenomena in the universe. The most common scenario involves a white dwarf in a close binary system with a main sequence star or a red giant. The white dwarf's gravity can pull material from the companion, drawing a stream of hydrogen-rich gas from the companion's outer layers. This material spirals inward and forms an accretion disk around the white dwarf. As the material accumulates on the white dwarf's surface, it is compressed and heated. When the temperature and pressure reach a critical point, the accumulated hydrogen ignites in a thermonuclear flash, a nova. A nova is not a supernova. The white dwarf is not destroyed. Instead, the surface layer of hydrogen is blasted away in a brief, brilliant eruption. The white dwarf survives, and the process can repeat, sometimes many times over thousands of years. These are called recurrent novae. The star RS Ophiuchi, located about 5,000 light-years away, has been observed to erupt as a recurrent nova at least 7 times since 1898, with the most recent eruption occurring in August 2021. In some binary systems, the transfer of mass can push the white dwarf toward the Chandrasekhar limit. If it reaches or exceeds 1.4 solar masses, the white dwarf undergoes a catastrophic thermonuclear explosion, a Type 1a supernova. Unlike a core collapse supernova, which leaves behind a neutron star or black hole, a Type 1 supernova completely destroys the white dwarf. Nothing remains. The entire mass of the star is converted into energy, light, and expanding debris. Type 1. A supernovae are among the most important tools in observational cosmology. Because they all occur at roughly the same mass threshold, they produce roughly the same peak luminosity, making them excellent standard candles, objects of known brightness that can be used to measure distances. By comparing the observed brightness of a Type 1 supernova with its known intrinsic brightness, astronomers can calculate how far away it is. This technique was used in the late 1990s by 2 independent teams, the Supernova Cosmology Project and the High Z Supernova Search Team, to discover that the expansion of the universe is accelerating. The leaders of these teams, Saul Perlmutter, Brian Schmidt, and Adam Rees, were awarded the Nobel Prize in Physics in 2011. When a neutron star exists in a binary system with a normal star, the results can be equally dramatic. Matter flowing from the companion onto the neutron star can form an accretion disk and produce X-ray binaries, systems that emit enormous amounts of X-ray radiation as the infalling material is heated to millions of degrees. These systems are among the brightest X-ray sources in the sky. In low-mass X-ray binaries, the companion star is typically a small, low-mass star. The transfer of matter is slow and steady, and the accretion disk is relatively stable. In high-mass X-ray binaries, the companion is a massive star with a strong stellar wind. The neutron star captures material from this wind, producing variable X-ray emission that can fluctuate dramatically over time. X-ray bursts occur when the material accumulating on a neutron star's surface reaches a critical density and temperature, triggering a thermonuclear explosion, similar to a nova on a white dwarf, but occurring under the extreme conditions of a neutron star's surface gravity. These bursts last only seconds to minutes, but can release as much energy as the sun emits in a week. In the most extreme binary interactions, 2 compact objects, 2 neutron stars, or a neutron star and a black hole, can orbit each other in a gradually tightening spiral, losing energy through the emission of gravitational waves. Over millions of years, the orbit shrinks until the two objects finally merge. The merger of two neutron stars, as observed in the gravitational wave event GW170817, produces a kilonova, a burst of electromagnetic radiation powered by the radioactive decay of heavy elements newly forged in the merger. The merger of a neutron star with a black hole has been detected as well. In January 2020, the LIGO and Virgo collaborations announced the detection of GW2, 00105 and GW200115, two gravitational wave events consistent with neutron star black hole mergers. These events were quieter and dimmer than the neutron star merger of GW170817, and no electromagnetic counterpart was detected, suggesting that the black holes in these systems may have swallowed the neutron stars whole without producing a visible explosion. Binary interactions add a layer of complexity and drama to the stellar graveyard. Dead stars do not simply cool and fade in isolation. They interact, accrete, explode, merge, and transform. The graveyard is not still. It is dynamic, violent, and endlessly creative, producing phenomena that single stars, living or dead, could never produce alone. The stellar graveyard contains objects that have been observed, measured, and cataloged, but it also contains, or may contain, objects that exist at the edge of theory, predicted by physics but not yet confirmed by observation. These hypothetical remnants are some of the most fascinating ideas in modern astrophysics, and they remind us how much of the universe remains unknown. One of the most intriguing theoretical objects is the quark star. In a neutron star, matter is compressed to the point where atoms no longer exist. Protons and electrons have merged into neutrons, but what if the compression goes further? Inside the cores of the most massive neutron stars, the pressure and density may become so extreme that even neutrons break apart. Neutrons are made of quarks, specifically 2 down quarks and 1 up quark. Under sufficient pressure, the quarks might be liberated from their confinement within neutrons, forming a new state of matter. Quark matter, also known as quark-gluon plasma. A star composed primarily of this quark matter would be a quark star, smaller and denser than a neutron star, but not quite a black hole. Theoretical models suggest that a quark star could be as small as a few kilometers in diameter, even smaller than a typical neutron star. Its properties would be subtly different from those of a neutron star, including differences in its cooling rate, its maximum mass, and the pattern of gravitational waves it would emit during a merger. No quark star has been definitively identified, but there are candidates. Some compact objects appear to be slightly too small or too dense to be easily explained as ordinary neutron stars. The object are XJ 1856.5-3754, initially measured to be unusually small for a neutron star, was considered a possible quark star candidate, though subsequent observations have complicated this interpretation. If quark stars exist, they might also contain an even more exotic form of matter, strange quark matter. In normal matter, quarks come in 6 varieties, or flavors, but ordinary matter contains only 2, up quarks and down quarks. Under extreme conditions, some of these quarks might convert to strange quarks, producing a mixture of up, down, and strange quarks known as strange matter. The strange matter hypothesis, proposed by physicist Edward Witten in 1984, suggests that strange matter might actually be the most stable form of matter in the universe, more stable than the ordinary nuclear matter that makes up atoms. If the strange matter hypothesis is correct, it has extraordinary implications. A piece of strange matter that came into contact with ordinary matter would convert that matter into more strange matter, a kind of cosmic contagion. A strange star would be an object composed entirely of this material, and if a piece of it were ever ejected into space, it could theoretically convert any neutron star it touched into a strange star as well. This is one of the more speculative ideas in physics, and there is currently no observational evidence that strange matter exists. But it remains a genuine possibility, lurking at the edges of what we know about the behavior of matter at extreme densities. Another theoretical object is the electro-weak star. In the standard model of particle physics, two of the four fundamental forces, electromagnetism and the weak nuclear force, are actually different aspects of a single underlying force, the electro-weak force. At sufficiently high temperatures, the distinction between these forces disappears. Some theorists have proposed that during the collapse of a massive star, before a black hole fully forms, there may be a brief intermediate phase in which the temperatures at the core are high enough to restore the electro-weak symmetry. The energy released during this phase could temporarily halt the collapse, producing a transient object called an electro-weak star. Such an object would last for only millions of years, brief by cosmic standards, before eventually completing its collapse into a black hole. No electro-weak star has been observed, and the concept remains firmly in the realm of theoretical physics. The preon star is perhaps even more speculative. Preons are hypothetical particles that are smaller than quarks, the idea being that quarks themselves might be made of even tinier constituents. If preons exist, and if matter can be compressed to the point where quarks break down into preons, then a preon star, a stellar remnant composed of preon matter, could theoretically exist. It would be extraordinarily tiny, perhaps the size of a basketball, yet contain the mass of a star. There is no evidence that preons exist, and most physicists consider preon models to be unlikely. But the idea illustrates how much we still do not know about the ultimate structure of matter. Thorne-Zhitkov objects, unlike the others on this list, are not purely theoretical. They may actually exist. Proposed in 1977 by physicists Kip Thorne and Anna Zhitkov, a Thorne-Zhitkov object is a red supergiant star with a neutron star at its core. The idea is that in a close binary system, a neutron star could spiral inward and be swallowed by its companion red supergiant, settling into the center of the larger star. The result would be an object that looks like a normal red supergiant from the outside, but has a neutron star hidden at its heart, influencing the nuclear reactions in the surrounding material. In 2014, astronomers reported a candidate Thorne-Zhitkov object, a red supergiant in the small Magellanic Cloud called HV 2112. The stars showed unusual abundances of certain elements, rubidium, lithium, and molybdenum, that are predicted by the Thorne-Zhitkov model, but difficult to explain through normal stellar evolution. The identification is not yet confirmed, and further observations are needed. But if HV2112 is indeed a Thorne-Zhitkov object, it would represent one of the strangest hybrids in the stellar graveyard, a dead star living inside a living star. The concept of a frozen star is another theoretical curiosity. In the original interpretation of general relativity, before the term black hole was coined by John Wheeler in 1967, collapsing objects were sometimes referred to as frozen stars. From the perspective of a distant observer, an object falling toward the event horizon of a black hole appears to slow down and freeze at the boundary, never quite crossing it. In this sense, the exterior of a black hole is forever decorated with the frozen images of everything that has ever fallen into it, a gallery of arrested motion, captured at the edge of infinity. While the falling observer experiences no freeze, they cross the event horizon and continue falling. The outside universe never sees them disappear. They are, from our perspective, frozen in time. There's also the idea of a boson star, a hypothetical object made not of ordinary fermions like protons, neutrons, and electrons, but of bosons, particles like photons that obey different quantum statistics. If certain types of hypothetical bosonic particles exist, axions for instance, they could, in theory, gravitationally clump together to form stable, macroscopic objects. A boson star would have no solid surface, no event horizon, and no singularity. It would be a kind of gravitationally bound cloud of quantum particles. Some physicists have speculated that what we currently identify as supermassive black holes at the centers of galaxies might actually be extremely massive boson stars, though there is no strong evidence for this. The stellar graveyard, it turns out, may contain objects we have not yet imagined. The boundaries of our knowledge are drawn by the limits of our observations and the reach of our theories. Beyond those boundaries, anything consistent with the laws of physics might exist, and in a universe as vast and old as ours, the improbable has had plenty of time to become real. Dead stars do not only emit light, they emit gravity. And in the most extreme circumstances, when compact objects collide, merge, or undergo violent rearrangements, they produce ripples in the fabric of space-time itself. These are gravitational waves, and their detection has opened an entirely new way of perceiving the universe. Gravitational waves were predicted by Albert Einstein in 1916 as a consequence of his general theory of relativity. But they were so faint, so incredibly weak by the time they reached Earth, that Einstein himself doubted they could ever be detected. It took a century of technological development to prove him wrong. On September 14, 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected gravitational waves for the first time. The signal, designated GW150914, was produced by the merger of two black holes roughly 1.3 billion light-years from Earth. The two black holes, with masses of about 36 and 29 times the mass of the Sun, had been orbiting each other in a gradually tightening spiral, emitting gravitational waves as they did so. In the final fraction of a second, they merged into a single black hole with a mass of about 62 solar masses. The missing 3 solar masses, roughly the equivalent of 6 trillion kilograms, were converted entirely into gravitational wave energy. The signal lasted less than a second. The peak gravitational wave power, in that final instant, was greater than the combined light output of all the stars in the observable universe. For a brief moment, 2 dead stars colliding in the dark outshone everything. LIGO detected this signal by measuring changes in distance so small they are almost beyond comprehension. The detector consists of 2 perpendicular arms, each 4 kilometers long. A gravitational wave passing through Earth stretches one arm while compressing the other by an amount smaller than the diameter of a proton. LIGO is capable of measuring these changes. It is the most precise measuring instrument ever built by humanity. The discovery was announced on February 11, 2016, and was immediately recognized as one of the most significant achievements in the history of physics. Rainer Weiss, Barry Barish, and Kip Thorne were awarded the Nobel Prize in Physics in 2017 for the detection. Since that first detection, LIGO and its European counterpart, Virgo, have observed dozens of gravitational wave events, mergers of black holes, mergers of neutron stars, and possible mergers of neutron stars with black holes. Each event reveals information about the masses, spins, and distances of the merging objects. Some have been surprising. The detection of GW190521, announced in 2020, revealed a merger between 2 black holes with masses of about 85 and 66 solar masses, producing a final black hole of roughly 142 solar masses. This was significant because the heavier of the two black holes fell within the so-called pair instability mass gap, a range of masses between about 65 and 130 solar masses, where standard stellar evolution theory says black holes should not form. Its existence suggested either a non-standard formation pathway or a previous merger that had already built up the mass. The detection of gravitational waves from neutron star mergers has been equally transformative. The event GW170817, the first neutron star merger detected, was accompanied by a gamma-ray burst, an optical kilonova, and emissions across the entire electromagnetic spectrum. For the first time, astronomers observed a single cosmic event in both gravitational waves and light. This marked the beginning of multi-messenger astronomy, the use of multiple types of signals to study the universe. Gravitational waves carry information that light cannot. They reveal the masses and spins of the merging objects directly. They are not absorbed or scattered by intervening matter. They pass through dust, gas, and galaxies unimpeded. They allow us to study events that produce no light at all, such as the mergers of two black holes in the void between galaxies. And they provide a completely independent way to measure the expansion rate of the universe because the gravitational wave signal from a merger encodes the distance to the source, while the electromagnetic counterpart, if detected, encodes the recession speed. Future gravitational wave detectors, such as the space-based LISA mission, planned by the European Space Agency for launch in the 2030s, will extend our sensitivity to lower frequencies, allowing the detection of mergers between supermassive black holes at the centers of galaxies, as well as the inspiral of stellar mass compact objects into supermassive black holes. These observations will probe the strongest gravitational fields in the universe and may reveal new physics at the intersection of gravity and quantum mechanics. Dead stars, even after they have ceased to emit light, continue to shape the universe through gravity. Their mergers send ripples across the cosmos that carry the stories of their deaths to instruments billions of light years away. In this sense, the graveyard is never truly silent. It hums. The universe is 13.8 billion years old. That is an immense span of time by human standards, but it is only the beginning. The universe will continue to exist for far longer, and the stellar graveyard over these vast timescales will undergo transformations that make the current age of the cosmos seem like an eye blink. In the current epoch, stars are still forming. Giant molecular clouds collapse under gravity, igniting new fusion reactions, producing new stars. But this era of star formation will not last forever. The supply of hydrogen gas in galaxies is gradually being depleted, converted into stars, locked in stellar remnants, or heated to temperatures where it can no longer collapse. Models of galaxy evolution suggest that the rate of star formation in the Milky Way has already declined significantly from its peak, which occurred roughly 10 billion years ago. Within the next 100 billion years or so, the last stars will form, and the era of stellar luminosity will draw to a close. When the last stars die, the universe will enter what physicists call the degenerate era, a period dominated by stellar remnants. White dwarfs, neutron stars, and black holes will be the only surviving remnants of what was once a cosmos full of light. Of these, white dwarfs will be the most numerous. In the degenerate era, white dwarfs will continue their slow cooling. Over trillions of years, their temperatures will drop from thousands of degrees to hundreds to tens, and eventually toward absolute zero. Their glow will fade from white to yellow, to red to deep infrared, and eventually to nothing visible at all. As they cool, The crystallization that has already been observed in some white dwarfs will progress further. The carbon and oxygen in their interiors will solidify into a crystalline lattice, a cosmic diamond, dark and cold, drifting through a dark and cold universe. These crystallized white dwarfs, sometimes whimsically called black dwarfs, would be the final state of a low to medium mass star, the ultimate endpoint of a journey that began with a cloud of gas collapsing under gravity billions or trillions of years earlier. But here's the remarkable thing. No black dwarf exists yet. The universe is not old enough. Even the oldest white dwarfs in the Milky Way, those that formed 11 or 12 billion years ago, are still warm. They still glow faintly in the deep infrared. The cooling time required for a white dwarf to become a true black dwarf, cold, dark, no longer emitting any detectable radiation, is estimated to be on the order of a quadrillion years. That is 10 to the power of 15 years. The current age of the universe is approximately 1.38 times 10 to the power of 10 years. The universe would need to be roughly 100,000 times older than it currently is before the first black dwarf would form. This means that black dwarfs are objects that physics predicts with high confidence, but that the universe has not yet had time to create. They are ghosts of the future, the eventual, inevitable fate of every white dwarf in existence, but a fate that lies so far ahead that no human concept of time can comfortably contain it. In the degenerate era, these cooling white dwarfs, and eventually black dwarfs, will drift through a universe that has grown dark and sparse. Galaxies will have merged or dispersed. Stars will have ceased to form. The cosmic background radiation will have redshifted to unimaginably long wavelengths, carrying almost no energy. The only sources of light will be the occasional flicker of a collision or accretion event involving compact objects. Over even longer timescales, trillions upon trillions of years, gravitational interactions within the remnants of galaxies will gradually eject some objects into intergalactic space, while others spiral inward toward the central supermassive black hole. The galaxy, as a gravitational structure, will slowly evaporate. After roughly 10 to the power of 19 to 10 to the power of 20 years, most stellar remnants will have been ejected, and the central black hole will be left alone, surrounded by a thin halo of escaping objects. The white dwarfs and black dwarfs that have been ejected will drift through the void between galaxies, or rather, through the void between the remnants of what were once galaxies. They will cool further. They will interact with almost nothing. They will be, for all practical purposes, the loneliest objects in the universe. But even these dark, crystallized remnants will not last forever. On timescales of roughly 10 to the power of 32 to 10 to the power of 40 years, depending on whether protons decay, as some grand unified theories predict, the very matter of these objects will begin to break down. Protons and neutrons, the building blocks of all atomic nuclei, may themselves be unstable on sufficiently long timescales. If proton decay occurs, then over these incomprehensible spans of time, the crystalline matter of the black dwarfs will slowly disintegrate, proton by proton, into lighter particles, radiation, and eventually nothing. If protons do not decay, and this is still an open question in physics, then black dwarfs will persist for even longer, but they will still not last forever. Over time scales of roughly 10 to the power of 65 to 10 to the power of 76 years, quantum tunneling events will cause the nuclei within the black dwarf to slowly undergo fusion. Cold fusion, driven not by temperature or pressure, but by the sheer probability of quantum tunneling over vast time scales. These tunneling events will gradually convert the matter in the black dwarf into iron-56, the most stable nucleus, releasing tiny amounts of energy in the process. The black dwarf will, imperceptibly slowly, transform itself into a ball of iron, the same element that ended the life of the massive star that preceded the supernova, now appearing at the very end of the story of the lowest mass stars as well. And then, on even longer timescales, the iron itself may undergo further quantum tunneling events, eventually collapsing into a tiny black hole, which would then evaporate through Hawking radiation. Or, if protons do decay, the black dwarf will simply dissolve into a mist of elementary particles and photons, dissipating into the void. These timescales are so vast that they make the current age of the universe seem like less than a heartbeat. The universe is 13.8 billion years old. The first black dwarf will not form for another quadrillion years. The last black dwarf will not dissolve for 10 to the power of 76 years or more. Between now and then lies a span of time so incomprehensibly long that no metaphor can do it justice. If the current age of the universe were a single second, the time until the last black dwarf vanishes would be longer than the current age of the universe itself, repeated more times than there are atoms in the observable universe. And yet, physics predicts it. The equations are clear, the processes are understood. The fate of every white dwarf in existence is to cool, crystallize, darken, and eventually, in one way or another, cease to exist. The graveyard will empty itself, given enough time. But enough time is a quantity so large that even the universe, vast and ancient as it is, has barely begun to approach it. The Milky Way galaxy, our home, is estimated to contain between 100 billion and 400 billion stars, but it also contains a vast population of stellar remnants, the dead stars that have accumulated over the galaxy's roughly 13 billion year history. Counting these remnants is not easy, because most of them are faint or invisible, but astronomers have made estimates, and the numbers are striking. The most numerous remnants are white dwarfs. Current estimates suggest that the Milky Way contains approximately 10 billion white dwarfs. This is a significant fraction of all stellar remnants, and reflects the fact that most stars, all those with initial masses between about 0.5 and 8 solar masses, end their lives as white dwarfs. Since the vast majority of stars fall within this mass range, white dwarfs are by far the most common endpoint. The nearest known white dwarf to Earth is Sirius B, at a distance of about 8.6 light-years. But there are several other white dwarfs within 20 light-years, including Van Maenen's star, one of the first white dwarfs ever identified, located about 14 light-years away. Procyon b, the companion of the bright star Procyon, is also a white dwarf, located roughly 11.5 light-years from Earth. Neutron stars are rarer. The Milky Way is estimated to contain roughly 100 million to 1 billion neutron stars, far fewer than white dwarfs, because the stars that produce neutron stars, those with initial masses above about 8 solar masses, are themselves much rarer. Only a small fraction of these neutron stars are visible as pulsars. Perhaps 200,000 or so are currently active, though only about 3,000 have been detected. Stellar mass black holes are estimated to number roughly 100 million to 1 billion in the Milky Way. Like neutron stars, they are produced by the most massive stars, but the precise boundary between a neutron star and a black hole remnant depends on the details of the supernova and the mass of the collapsing core. Most of these black holes are completely dark, solitary objects drifting through the galaxy with no companion star, no accretion disk, and no detectable emission of any kind. The Milky Way also contains one supermassive black hole at its center, Sagittarius, a star, with a mass of roughly 4 million times the mass of our Sun. This is not a stellar remnant in the traditional sense. Supermassive black holes are thought to have formed through different processes, possibly involving the direct collapse of massive gas clouds in the early universe or the merger of many smaller black holes over time. But Sagittarius A star sits at the gravitational center of the galaxy, and its presence shapes the orbits of stars in the galactic core. In 2022, the Event Horizon Telescope collaboration released the first image of Sagittarius A star, a glowing ring of superheated gas surrounding the shadow of the black hole's event horizon. The image confirmed decades of indirect observations and provided a visual confirmation of the supermassive black hole at the heart of our galaxy. Beyond these major categories, the Milky Way contains planetary nebulae in various stages of expansion and dispersal, supernova remnants in various stages of cooling and fading, and a diffuse enrichment of heavy elements throughout the interstellar medium, the accumulated legacy of billions of years of stellar death. Every cloud of gas that collapses to form a new star is enriched with the products of previous stellar generations. The Sun itself is a third-generation star, formed from material that has been processed through at least 2 previous cycles of stellar birth, death, and enrichment. The galaxy, in a very real sense, is built on the graves of its ancestors. Every new star inherits the chemical legacy of the dead. Every planet, every moon, every grain of dust carries atoms that were once inside a star that no longer exists. The living and the dead in the Milky Way are inseparable. The deaths of stars produce some of the most visually spectacular phenomena in the universe. While most stellar remnants are faint or invisible, the processes surrounding their formation and evolution paint the cosmos with extraordinary color and light. Planetary nebulae, as we explored earlier, are among the most colorful objects in the sky. Their hues are determined by the elements present in the expelled gas and the energy of the radiation illuminating them. Doubly ionized oxygen produces a vivid blue-green glow at a wavelength of 500.7 nanometers, one of the most recognizable spectral lines in astronomy, sometimes called the Nebulium line, because it was once attributed to a hypothetical element before being correctly identified. Hydrogen produces red light through the Balmer alpha line at 656.3 nanometers. Nitrogen contributes additional red emission. The interplay of these elements creates the spectacular color palettes seen in Hubble and JWST images. Supernova remnants glow in different ways. The hot, shocked gas at the expanding shock front emits primarily in X-rays, too energetic for the human eye to see, but vividly captured by space-based observatories like Chandra. At longer wavelengths, the cooler filaments of ejected material emit invisible light, hydrogen red, oxygen green, sulfur deep red. Radio emission reveals the structure of the magnetic fields within the remnant. Infrared observations reveal warm dust mixed into the expanding debris. The accretion disks around black holes and neutron stars glow with their own fierce light. The material in these disks is heated to millions of degrees, producing intense X-ray emission. When this X-ray light is translated into false color images for human consumption, the result is often a swirl of blue and violet, colors chosen to represent the high-energy radiation that our eyes cannot naturally perceive. Kilonovae, the explosions produced by merging neutron stars, produce a distinctive reddish-orange glow. This color comes from the radioactive decay of freshly synthesized heavy elements, particularly those in the lanthanide series of the periodic table. The kilonova associated with GW 170817 was described by astronomers as having a deep blue color in the first hours after the merger, shifting to red over the following days as the expanding debris cooled and the opacity increased. Even white dwarfs, in their quiet way, contribute to the visual palette of the cosmos. A young, hot white dwarf emits strongly in the ultraviolet, appearing blue-white. As it cools over billions of years, its color shifts from white to pale yellow, then to deeper yellow, orange, and eventually a dim red before fading entirely from view. The color of a white dwarf is, in effect, a clock, a visual indicator of how long ago the star that produced it died. The colors of the stellar graveyard are not merely aesthetic, they carry information. Every wavelength of light tells a story about temperature, composition, density, and motion. The red glow of a hydrogen filament reveals a cloud of gas expanding at a particular speed. The blue-green flash of ionized oxygen marks the boundary where a dying star's radiation meets its expelled atmosphere. The X-ray blaze of an accretion disk measures the temperature of matter being devoured by gravity. When you look at a photograph of a planetary nebula or a supernova remnant, you are looking at a portrait of death, painted in the light of atoms that were forged inside a star, released by its destruction, and illuminated by the energy of its remnant. Every color is a chemical signature. Every glow is a physical process. And the result, purely by accident, is breathtaking beauty. Stars are the universe's factories. During their lifetimes, they forge new elements in their cores through nuclear fusion. And when they die, they return those elements to the cosmos, enriching the interstellar medium with the raw materials for planets, moons, asteroids, comets, water, and life. The elements created by a star depend on its mass. The lightest stars, those with masses below about half the sun's, never progress beyond hydrogen fusion. They produce helium and nothing else. When they eventually die, which, as we discussed, has not yet happened for any of them, they will return only hydrogen and helium to the universe. Stars like our Sun fuse hydrogen into helium, and then helium into carbon and oxygen. When they shed their outer layers as planetary nebulae, they enrich the interstellar medium with these elements, along with nitrogen and trace amounts of heavier elements produced through slower nuclear processes. More massive stars, those above about 8 solar masses, fuse elements all the way up to iron in their cores. When they explode as supernovae, they scatter these elements into space: carbon, nitrogen, oxygen, neon, magnesium, silicon, sulfur, calcium, and iron. But the supernova explosion itself produces even more. In the extreme conditions of the explosion, temperatures of billions of degrees, neutron fluxes of unimaginable intensity, elements heavier than iron are created through rapid neutron capture, or the R process. This is how the universe produces gold, platinum, uranium, and dozens of other heavy elements. Neutron-star mergers, as confirmed by the observation of GW 170817, are another major site of R-process nucleosynthesis. The collision of two neutron stars produces conditions even more extreme than a supernova, and the quantities of heavy elements produced can be staggering. A single neutron star merger can produce several Earth masses of gold and several Earth masses of platinum. The result of all this stellar chemistry is the periodic table as we know it. Hydrogen and most helium were produced in the Big Bang, roughly 13.8 billion years ago. Essentially everything else, every element from lithium to uranium and beyond, was produced inside stars or during stellar explosions. The carbon in organic molecules, the oxygen in water, the silicon in rocks, the iron in blood, the calcium in bones, the phosphorus in DNA. All of it came from stars. This process of enrichment is cumulative. Each generation of stars incorporates the products of previous generations and adds its own contributions when it dies. The Sun, as a third-generation star, contains elements produced by multiple generations of stellar ancestors. The planets of our solar system, Earth included, are made from this enriched material. The metallicity of a star, a measure of the fraction of its mass that consists of elements heavier than hydrogen and helium, is a record of how many previous stellar generations have contributed to the material from which it formed. Old stars, formed early in the galaxy's history when few heavy elements had been produced, have low metallicity. Young stars, formed from material enriched by billions of years of stellar death, have higher metallicity. The Sun's metallicity is about 1.3%, meaning that about 1.3% of its mass consists of elements heavier than helium. That small percentage contains every element on the periodic table. There is a quiet grandeur in this. The deaths of stars are not waste. They are not destruction. They are the mechanism by which the universe builds complexity. Without stellar death, the cosmos would contain nothing but hydrogen and helium, an infinite sea of simple gas with no planets, no water, no carbon, no life, no one to look up at the stars and wonder what they are made of. The graveyard of dead stars is, in this sense, a garden. Everything that grows in the universe grows from the soil of stellar death. Humanity has always given names to the dead, and in a way, we have done the same with dead stars. The objects in the stellar graveyard carry designations, catalog numbers, and sometimes nicknames that reflect the wonder, humor, and reverence with which astronomers have approached them. The Crab Nebula, the remnant of the supernova of 1054 AD, was named by the 3rd Earl of Rosse, William Parsons, in the 1840s. Observing it through his enormous telescope, the largest in the world at the time, he thought the nebula's shape resembled a crab. The name stuck, though modern photographs reveal a structure far more complex and beautiful than any crustacean. The Jewel Box Cluster, NGC 4755, is a young star cluster rather than a remnant, but its name reflects the human tendency to see beauty in the sky and name it accordingly. Among actual remnants, the nicknames are equally evocative. The Ghost of Jupiter, NGC 3242, is a planetary nebula that appears roughly the same angular size as Jupiter when viewed through a small telescope. The Eskimo Nebula, the Owl Nebula, the Dumbbell Nebula, the Hourglass Nebula, each name captures a visual impression, a moment of recognition, a human seeing a familiar shape in an unfamiliar place. The White Dwarf, BPM 37093, with its crystallized carbon interior, was nicknamed Lucy, after the Beatles' song Lucy in the Sky with Diamonds. The name was given informally by the astronomers who studied it, and it captured the public imagination. A diamond star, floating in the dark, it is the kind of image that blurs the line between science and poetry. Some designations are more prosaic. PSRB 1919+21, the first pulsar ever detected, carries a name that encodes its position on the sky and nothing more. GW 150914, the first gravitational wave event, is named for the date of its detection. These clinical labels serve the needs of precision, but behind each one lies a moment of discovery. A human being looking at data and realizing for the first time that something extraordinary had been found. Jocelyn Bell Burnell, who discovered the first pulsar, later described the moment with characteristic understatement. She noticed a bit of scruff in the data, a repeating signal that did not match any known source. Her curiosity led to one of the most important discoveries in 20th century astronomy. The fact that she was a graduate student and a woman in a field dominated by men adds a layer of human significance to the story. The Nobel Prize she did not receive is as much a part of the history of pulsars as the pulsars themselves. The naming of celestial objects is, in its way, an act of claiming. By giving a name to a dead star or a distant nebula, we assert a relationship with it. We declare that it matters, not just as a point of data, but as a thing worthy of attention, worthy of a name. And in doing so, we weave the dead stars into the human story. Ancient civilizations did this instinctively. The supernovae of 1054, 1572, and 1604 were all recorded by human observers who saw them not as scientific phenomena, but as portents, signs, disruptions in the heavenly order. The Chinese astronomers who recorded the guest star of 1054 could not have known that what they were seeing was the death of a massive star, the birth of a neutron star, and the creation of a glowing nebula that would still be visible 1,000 years later. But they looked up, and they wrote it down. And because they did, we know the age of the Crab Nebula with remarkable precision. Tycho Brahe's observation of the 1572 supernova shook the foundations of European astronomy. The idea that new stars could appear in the heavens, that the cosmos was not fixed and unchanging, was a philosophical earthquake. The death of a star, observed from Earth, helped birth a new understanding of the universe. Throughout human history, the sky has been a mirror for our deepest questions. Are we alone? Is the universe eternal? What happens after the end? The stellar graveyard offers answers, not in the form of reassurance, but in the form of evidence. Stars die. But from their deaths come new elements, new structures, new possibilities. The universe does not end with death. It transforms. There is a quiet comfort in this if you choose to find it. The atoms in your body, the carbon, the oxygen, the nitrogen, the iron, were forged in the cores of stars that died before our sun was born. You are, in a very literal sense, made of dead stars. The graveyard is not somewhere out there beyond the reach of your life. It is inside you. It is you. In the quietest corners of the stellar graveyard, there is something worth sitting with. Not a fact, not a measurement, but a feeling. The feeling of a universe that is, very slowly, winding down. The universe is not dying in the way a star dies, suddenly, violently, with a flash of light. It is aging, slowly. The rate of star formation has declined. The supply of hydrogen is diminishing. The galaxies are drifting apart, carried by the expansion of space itself. And the stellar remnants, the white dwarfs, the neutron stars, the black holes, are accumulating one by one in the dark. This does not mean the universe is sad. Sadness requires a perspective, a sense of loss, a consciousness to feel it. The universe simply is. It does what physics requires. It follows its equations, its laws, its probabilities. And those equations say that, given enough time, all the fires will go out. But between now and then, between this moment and the last photon emitted by the last black hole evaporating in an unfathomably distant future, there is time. Immense amounts of time. Time for new stars to form. Time for planets to coalesce. Time for life to arise, thrive, wonder, and question. The fact that the universe will eventually grow dark does not diminish the light that exists now. If anything, it makes it more precious. The white dwarfs cooling in the dark are not failures. They are the natural conclusion of lives well lived, stars that burned steadily for billions of years, producing the energy that warmed planets and the elements that built them. The neutron stars spinning in the void are not broken. They are the most extreme expression of matter's resilience, holding together under pressures that would crush anything else. The black holes drifting silently through the galaxy are not empty. They carry within them the mass and memory of everything that ever fell across their horizons. Even the hypothetical black dwarfs, the objects that do not yet exist, that will not exist for a quadrillion years, carry a kind of dignity. They represent the very last stage of a process that began with a cloud of gas, continued through billions of years of nuclear fusion, transitioned through a planetary nebula or a supernova, settled into a white dwarf, and will eventually crystallize into a dark, cold, diamond-hearted sphere drifting through an empty universe. That journey, from cloud to crystal, is one of the longest and most complete stories in all of physics. The silence between the dead stars is not empty. It is full of potential. The potential for the heavy elements scattered by supernovae to gather into new worlds, for the gravitational waves from merging compact objects to reveal new truths about the fabric of reality, for the slow cooling of white dwarfs to teach us about the history of the galaxy. Even the darkest corners of the graveyard are illuminated by what they can tell us, if we know how to look. There is a passage often attributed to the physicist Richard Feynman, though its exact origin is debated. The universe is not only queerer than we suppose, but queerer than we can suppose. The stellar graveyard embodies this sentiment. It contains objects that defy everyday intuition. Matter denser than atomic nuclei, magnetic fields strong enough to reshape the vacuum of space, time frozen at the boundaries of collapsed stars, diamonds the size of worlds, signals sent by dead stars that are more precise than the best clocks ever built by humanity. And yet, for all their strangeness, these objects follow the same laws of physics that govern the fall of an apple and the orbit of the moon. They are not separate from the universe you inhabit. They are part of it. And so are you. The calcium in your bones was forged in a star that died in a supernova. The iron in your blood was created in the final moments of a massive star's life, just before the core collapsed. The gold in a ring may have been born in the collision of two neutron stars billions of years ago in a galaxy that no longer exists in its original form. Every atom in your body has a history that stretches back through multiple stellar generations, births and deaths, explosions and collapses, slow cooling and sudden catastrophe. You are not a visitor to the stellar graveyard. You are its product. And that, perhaps, is the most extraordinary fact of all. Not that stars die. Not that their remnants are strange and beautiful and extreme. But that from those deaths, from the ashes of ancient fires, from the debris of cosmic explosions, from the slow crystallization of dying embers, the universe built something that could look back at the stars and ask, "What are you?" The answer, it turns out, is, "You are us, and we are you." Reflective close. And so, we come to the end of our journey through the graveyard of dead stars. We visited the white dwarfs, those quiet embers, slowly cooling in the dark, some crystallizing into cosmic diamonds that will endure for trillions of years. We've watched the planetary nebulae expanding into space, painted in the light of oxygen and hydrogen, carrying the last breath of a dying star into the void. We've stood at the edge of supernovae, explosions so violent they outshine entire galaxies, yet so creative they seed the universe with every element heavier than iron. We've marveled at neutron stars, cities of compressed matter spinning hundreds of times per second, sending signals across the galaxy with a precision that rivals the finest clocks ever built. We've encountered magnetars, with magnetic fields strong enough to reshape the vacuum of space. We've peered into black holes, where matter vanishes behind horizons from which nothing returns. We've listened to the gravitational waves produced when dead stars collide, ripples in the fabric of space-time that carry the echoes of ancient violence across billions of light years. And we've looked forward to the degenerate era when the last stars will have died and the universe will be populated only by remnants. White dwarfs cooling into black dwarfs, neutron stars slowing into silence, black holes evaporating, photon by photon, over timescales that make the current age of the universe seem like less than a heartbeat. The graveyard of dead stars is vast, it is ancient, and it is beautiful. It is also inside you. Every atom of carbon, oxygen, nitrogen, calcium, and iron in your body was forged in the core of a star that no longer exists. You are made of stellar ash. You carry the legacy of the dead with every breath, every heartbeat, every thought. Tonight, as you settle in, as you let the weight of the day slip away, as your breathing slows and the world grows quiet, know this: the universe did not simply make you from dust, it made you from starlight, from supernovae, from the slow cooling of ancient embers and the violent collision of impossible objects. You are the graveyard's most extraordinary creation, a piece of the cosmos that can look back at itself and feel wonder. And that wonder is enough. It is more than enough. It is everything. If this journey has helped you unwind, or if it has given you something beautiful to carry into sleep, a quiet like or a tap on subscribe would mean the world. It helps other restless minds find their way here, one sleepy soul at a time. Thank you for being here tonight. Thank you for listening, and thank you for carrying a little bit of stardust with you. Wherever you go, sleep well. The stars, living and dead, will be here when you wake. Good night.